eigenvalues and eigenvectors. I just thought I would start by doing this revision question here. So can you please have a look at that matrix, and I want to find all the eigenvalues and then find the eigenvector corresponding to lambda equals 2. Now, hopefully, depending on whatever way you get your eigenvalues, you'll get the same results as me. And this one is actually a little shortcut. I'll show you the shortcut, but the long way should give you the same answer that I did in the last example. So, first thing we do is we put down our matrix and we write down our eigenvalue equation. Now, our eigenvalue equation is the determinant of a take away lambda I is equal to 0. So we take our matrix, we put the two straight lines on either side, and we take away lambda from each element on the diagonal, and we set that equal to 0. So that's what I've done. Now the reason this is already written is because that little 1 disappeared when I was writing it up the previous time I tried to film this video, so I've restarted it. Right, so this is the matrix we should have. And this is what we should have done when we expand along the top row. So remember, 2 take away lambda, then take away -5 because it's always a negative in here, and then plus 5 in here. Right, so this is the bit that I had my mistake in. So I'm just going to rub that out, and I'm going to continue on from here. Right, so it's AD take away BC, so that's 1 take away lambda multiplied by -4 take away lambda take away -4, which is just plus 4. Then plus 5, and then here you've got -1 multiplied by -4 take away lambda take away 1 plus 5, and then you've got -4 take away -1 times 1 take away lambda. Okay, now my advice would be to see these brackets you've done AD minus BC and always simplify them first, because it might be that there's an easy way out rather than having to multiply everything out. Sometimes it isn't though. Right, so let's multiply that out. So that's -4 take away lambda plus 4 lambda plus lambda squared plus 4 plus 5. And in this bracket you've got 4 plus lambda take away 1 plus 5. And then in this bracket we've got -4 plus 1 take away lambda. Right. As you can see, stuff has jumped about again, so let's see if anything's missing. Plus lambda squared plus 4. It's so annoying. Don't know why I started doing that. Right, so you've got 2 take away lambda, and then in this bracket you've got lambda squared plus 3 lambda, and then this 4 and 4 cancel each other out, so there's no term like that, right? Then you've got plus 5 of lambda plus 3, then you've got plus 5 of negative lambda take away 3. Right now, and sorry, I should have equal to 0 all the way up here. Right, so can you see that that thing there, and I'll show you by looking at it. if I take the negative out of this bracket here, it makes it take away 5, y plus 3 is equal to 0. And can you see these brackets are the same thing? And that's got 5 of them, and that's got negative 5 of them. So these two things are actually cancelling each other out, because that's like 5x, take away 5x. So these two things here cancel each other out. So what I'm left with is 2 take away lambda, lambda squared plus 3 lambda equals 0. Right, now that's nearly factorised. They're in brackets, that's what factorising means. So effectively using this method and spotting that bracket is going to be the same. There's a plus in there. And spotting that that bracket's the same effectively has allowed us to miss out multiplying everything out. Now you've got a common factor of lambda in here. It's actually 2 lambda, lambda plus 3 is equal to 0. So that means we've got our 3 eigenvalues. 2 take away lambda is equal to 0. So lambda equals 2. Lambda equals 0 for that middle bit, because that's just lambda on its own. And lambda plus 3 equals 0, which means that lambda equals negative 3. And I'm happy enough with that. Hopefully my pluses and negatives haven't started missing out lines and stuff, but it looks fine to me. Right, so the reason I know that that probably is right is the fact that in the question it asked me to find the eigenvector corresponding to lambda equals 2. So I know I should be getting an eigenvalue of lambda equals 2. Okay, so the next bit was then to find the eigenvector for that eigenvalue of 2. So when lambda equals 2, so remember what we do is we set up our eigenvector equation, which means we've got x1, x2, and x3 is equal to 0 there, right? And remember, you're taking away lambda from each of the diagonals again. Now if you wanted, you could just take away 2 there, because we know that lambda is equal to 2, but I'm just writing out the full working. Right, so there we are there. Hopefully nothing's going to... Oh, negative 4. That was me, not the computer this time. I'll take responsibility. Right, so we're taking away 2 from the diagonal, so that's going to be 0, 5, 5, negative 1, negative 1, negative 1. Sorry. And negative 1, 4, and negative 4, take away 2 is negative 6. So remember, what we want to do is make the bottom 3 elements here 0. Now, we've got a wee bit of an issue here. So this is another thing that could crop up in your eigenvector type question, right? And that's why I'm going through another example. Right now, I've got a 0 in here, and I would want that to be in there. So what I can do is just swap my rows around, if I'd prefer to do that. So let's do that. So I'm just going to swap these rows over before I do anything else, because it's going to be impossible for me to get 0 in here. So I'm just going to swap those rows around. And you can do that at any point if you think it's going to make the matrix work and make it upper triangular. Right, so by simply doing that, I have got the middle element to be 0. Right? Now, there is no way I can use row 1 and row 2 to make them 0. to make that 0. So that's why I've had to do that. Okay. So now I need to make this one 0. So top 2 rows look fine to me. -1, 1, -1, 0, 5, 5, x1, x2, x3 is equal to 0. Right. So I'm going to do R3 take away R1, because remember, that's what I always need to do to make that element 0. So R3 take away R1 would be 0, so that is 0. Right, 4 take away 1 is 3. -6 take away -1 is -5. Okay. One of my wee negative ones decided to go missing there, so that one in there should in fact be -1. So that element in there should in fact be 5. So yeah, again, I think it was easy when I used paper and pen. At least when I used pen, the mark stayed in the page. Anyway, and then it's gone again. This is going to be the death of me. Right, so last thing I've got to do is make this element in here 0, so I'll leave the top 2 rows the same. So that's just going to, I need to just add these 2 rows together. So that's row 3 plus row 2. So that's 0, 0, 0. Right. So then this middle equation tells me I've got -5x2 plus 5x3 equals 0. So that just means that 5x2 equals 5x3. Those are both in the 5 times table. So x2 equals x3. So that tells me that x2 equals 1 and x3 also equals 1. Because x3 is the number in front of x2 and x2 is the number in front of x3. Right then, that top equation, -x1 take away x2 take away x3 is equal to 0. So I'm just going to substitute in those 2 values. So that's -x1 take away 1 take away 1 is equal to 0. So -x1 take away 2 equals 0. So -x1 equals 2, which tells me that x1 is -2. So our eigenvector for lambda equals 2 is t multiplied by -2, 1, 1. There we go. So I hope you're happy with that and you got that answer. I know that the way I found the eigenvalues was just a wee trick involved there involving factorising, but hopefully it's not too bad. Right, so what we need to do is look at the other type of question. That's when I said there's this thing called degeneracy, and we've looked at degeneracy throughout maths. We looked at differential equations, all that kind of stuff, and that's when you've got something that's equal, so it looks like you're not going to get 3 eigenvectors, you're only going to get 2 eigenvectors. So let's have a look at this one here. So in order to get as many eigenvectors you should do, now it's not always possible to get that, they need to be linearly independent. So that means they need to be different. Right, so this is the example I'm going to use here. So I've got this matrix A, which is -2, 2, -3, 2, 1, -6, -1, -2, 0. So I'm going to find all the eigenvalues first, then try and find all the eigenvectors. So you can imagine this will take a little bit of time. Right, so eigenvalues. So I'm not going to bother writing down the equation, we should all know it by now. So is equal to 0. So the determinant of our matrix with lambda taken away from all the diagonals is equal to 0. Right, so let's expand across that top line then. So -2 take away lambda, 1 take away lambda, -6, -2, and that's negative lambda down the bottom. Take away 2 multiplied by 2, -6, -1, negative lambda, plus -3, so that's staying at negative, that's staying at take away 3 of 2, 1 take away lambda, -1, -2. We're saying that's equal to 0, and try not to forget that equal to 0. I know it takes so long to fit that into a page, so you might forget to put that in. Try and avoid doing it. I know I do it from time to time, just because I'm trying to fit it all in one line. Right, let's hope that nothing's vanished there. So -2 take away lambda, and then we're going to do AD take away BC. That's 1 take away lambda, multiplied by negative lambda, and that's going to be take away 12. Take away 2 times, well, that's going to be -2 lambda, take away 6, take away 3 times -2 lambda plus 1 times 1 take away lambda equals 0. So just about getting in the equals 0, the bit I should close that bracket. Right, as you can see, it is a lot to fit on one line. If you want to do it over 2 lines, it might make it a wee bit neater. Now I'm just going to sort out the brackets I've just worked out. So that's going to be negative lambda plus lambda squared take away 12. And here we've got -2, that's -2 take away 6. Oh, sorry, messed up my lambda. -2 lambda take away 6. Take away 3. And here we've got now is a case of me not being able to read my own writing. Sorry, 2 times -2, which is that bit there. That should be -4. That's not a lambda, that's just me being an idiot. Right, so in here we've got negative lambda take away 3. Right, now let's have a wee look and see if there's a wee trick we can do here, right? So now, can I factorise this bit in here? Yeah, I can. Well, I'm going to rewrite it in the other way first. And here, there's a common factor here of -2, so I can make that +4. Lambda plus 3. And here, that's if I take a common factor of -1, that makes that lambda plus 3. Cool. So if I factorise this and I get lambda plus 3, it's looking good. Right, so I factorise this c dt, and when you do c dt, it's a trinomial. You're adding to make -1, multiplying to make -12, so that gives you lambda take away 4, lambda plus 3, plus 4. lambda plus 3, plus 3, lambda plus 3. That should be equal to 0. So our common factor here is lambda plus 3. So if I take that out as a common factor, I've got negative 2 take away lambda, lambda plus 4, plus 4, plus 3 is equal to 0. You sort this stuff out in here. So it's negative 2 lambda, take away 8, take away lambda squared, take away 4 lambda, plus 7 is equal to 0. So lambda plus 3, that's negative lambda squared. Another wee mistake in here. No idea what's happened to me today. Let's go back. Right, so that should be, sorry, lambda take away 4 in there. So it's negative 2 lambda plus 8 take away lambda squared plus 4 lambda plus 7. Is equal to 0. Now, I don't like the fact that's a negative, so I'm just going to change the sign of everything in the bracket, and I can do that because it's equal to 0, so that's just lambda squared. Take away 2 lambda, take away 15. If I do CDT on that, it factorizes into lambda take away 5, lambda plus 3 equal to 0. So you've got your eigenvalues. Lambda equals 3, so lambda equals negative 3, lambda equals 5, and lambda equals negative 3. The reason I'm so trying to get this software to work and trying to get the device to stop messing about with negatives and positives is I need it for the double integration section because there's lots of diagrams in that. It's going to be a lot easier to use the diagrams on this than it is for me to try and draw the diagrams because you know what my drawing skills are like. But anyway, I've got two eigenvalues that are the same. So that means that there's degeneracy here. Because what do I do when I've got two eigenvalues that are the same? Because surely they're going to give me the exact same eigenvector. Right, so let's go on and do lambda equals negative 3. Now we know how to work out lambda is equal to 5. We know how to work out the eigen vector for that, so it shouldn't really be an issue. I'll come back and do that at the end. The one we're interested in is lambda being equal to 3. Okay, so for lambda equals negative 3, I don't know why I keep saying 3. Right, so this is where we get our eigenvector matrices out. So it's -2 take away 3, or -2 take away -3 actually, hold on. Let's get that right. -2 take away -3 to -3 to 1 take away -3, -6, -1, -2, 0 take away -3. So I've just not written down the -2 take away lambda, 1 take away lambda, 0 take away lambda thing. I've just chucked in a -3 straight away. So let's, okay, that's 1 to -3, 2, 4, -6, and -1, -2, 3. Right, so the first thing I need to do is make this element in here 0. So the way I'm going to do that is using R1 and R2. Hopefully negative signs don't disappear, and I think we're okay this time. So 1, 2, -3. Right now, so if I do R2 take away 2 R1, so that's going to give me 0. 1 of that take away 2 of that, well that's going to give me 0. 1 of that take away 2 of that, well that's going to give me 0. Okay, right. Right, then I've got this thing here. Well, I want to make that 0, so if I do R3 plus R1, remember this one here is always R1 and R3. Right, so that is 0. Well, that's going to be 0. And that's going to be 0. Right, so I've quite easily got my bottom 3 elements here to be 0. Now, that means we've got the following equation. x1 plus 2x2 take away 3x3 is equal to 0. Now, this is where you have as much freedom as you want to get your own eigenvectors, right? There's not a specific correct answer. There's 3 specific answers you can get from here. So you've just got to decide, well, I'm going to choose one of the variables to be 0 and then work out the eigenvector, and then choose another variable to be 0. So I'm just going to say when x1 equals 0, right? Because you get freedom to choose either or any of the 3 variables to be equal to 0. So you would have 2x2 take away 3x3 is equal to 0. So 2x2 equals 3x3. So that means that x2 is 3 and x3 is 2. So that would give me this eigenvector 0, 3, 2, right? But remember, this is for 2 eigenvalues. You've got repeated eigenvalues, right? So I need to get a second eigenvector if I can, right? So I'm just going to then choose when x2 is equal to 0. So that's x1 take away 3x3 is equal to 0. So x1 is 3x3. So that means that x1 is equal to 3 and x3 is equal to 1. Remember, we've already said x2 is equal to 0. So that means I've got 3, 0, 1. Now I've already used the letter T, so I'm just going to use a different letter S. So your eigenvalue, or your eigenvector, for lambda equals -3 is T of 0, 3, 2, no it's not, stop putting an equal sign in it. You know, 3, 2 plus S 3, 0, 1. And what we should always say is that T and S are not equal to 0. In any vectors, T is not equal to 0, or any eigenvector T is not equal to 0, because it would stop it being a vector and it would make it the 0 vector instead. And just for reference, if as you do this yourself, so that's -3, when lambda equals 5, T is 1, 2, or their eigenvector is T multiplied by 1 to -1. And that's what you should get. So please have a go working out lambda being equal to 5 as well for that one. Now, I am not going to ask you anything as tricky as that, but I just want to show you that's what happens if you get a repeated eigenvector. Sorry, a repeated eigenvalue. You end up with this eigenvector with two parts. Right, now this is the final bit in eigenvalues and eigenvectors, and it's a little bit long. That stuff there wasn't long enough for you and I didn't make enough mistakes in that. Here is another one. So it's all about, hopefully it's going to come, diagonalising a matrix. Now we diagonalise a matrix if we quickly want to calculate the power of a matrix. I know you're going to say quickly, no, but think about what a to the power of 12 would mean. That would mean you'd need to do that horrible matrix multiplication thing 12 times. If it was the power of 25, you need to do it 25 times, and that would take a long time. So what you can do is use the power of a diagonal matrix in order to do that. So we're only going to do this with 2 by 2 matrices. I'm not going to do it with 3 by 3 matrices, but the theory is exactly the same. Right, now, any matrix a to the power of n can be written as a diagonal matrix to the power of n. Now, a diagonal matrix is a matrix which has got only numbers on its lead diagonal like that. So that could be 4, 3, but it's got zeros on either side there. Now, the power of that is that if you do that to the power of 4, then all you need to do is make that to the power of 4 and that to the power of 4. There's no need to actually multiply stuff out loads and loads and loads of times. Right? Whereas if you've got a 4-element matrix, it's awful. Right, so this is our formula here. AN is equal to a matrix X, which we've got the inverse of, multiplied by a diagonal matrix to the power of n, and that's the power that we want to find A of, multiplied by this other matrix X. Now, the diagonal matrix is made up of the eigenvalues of matrix A. And X is made up as a matrix of eigenvectors of matrix A. Now, what you need to do is make sure that your eigenvectors and your eigenvalues line up, just like this. But I'll show you what this all means with an example, as I always do. Okay, let's look at our example. So our example is find the expression for a to the power of n such that a to the power of n equals x inverse multiplied by d to the power of n x when a is equal to the matrix 4, 2, 3, -1. And then hence we're going to calculate a to the power of 8. Right, so first thing you're going to do is work out the eigenvalues. It's 2 by 2, so these are fairly easy. So it's just the determinant of 4 take away lambda, 2, 3, negative 1 take away lambda is equal to 0. AD take away BC, so 4 take away lambda, negative 1 take away lambda, take away 6 is equal to 0. Multiply that out, negative 4 take away 4 lambda plus lambda plus lambda squared take away 6 is equal to 0. I'm going to write this down before I move the screen in case it messes everything up. So that means I've got lambda squared take away 3 lambda take away 10 is equal to 0. Okay, now as always, CDT 2 by 2 is so much easier than 3 by 3 because it's just a lovely little trinomial to factorise. So that's x take away 5, x plus 2 equal to 0. So lambda equals 5, sorry, lambda rather than x, and lambda equals negative 2. Right, so remember our diagonal matrix, in fact I'll call this lambda 1 and lambda 2 this time, it doesn't really matter. Our diagonal matrix is made up of our eigenvalues. So you get 0 and 0 here, and you put your eigenvalues in. Now your eigenvalues can go in either order. All that matters is that later on your eigenvectors correspond to it. So I'm just going to put it in as 5 in this bit, and negative 2 in this bit. Right, so that means that the eigenvector corresponding to 5 has to be in this column, and the eigenvector corresponding to negative 2 has to be in this column. Right, so eigenvectors. Two by two eigenvectors are dead easy. So we just take our matrix 4. And we take away lambda from the diagonal. And this time, because it's 2 by 2, we're multiplying by x1 and x2. We're saying that's equal to 0. I just go back and check my matrix, see if I've done anything wrong. I don't think I have. Right, now, so my eigenvalue, first thing I'm going to look at is lambda being equal to 5. So lambda equals 5. So that means I've got 4 take away 5, which is negative 1, 2, 3, negative 1 take away 5 is negative 6. x1, x2 is equal to 0. Then I need to make this element here 0, so it becomes upper triangular. But it should be fairly easy to do that. So that's just going to be R2 plus 3R1. Because one of those plus 3 of those would be 0. So 0, one of those plus 3 of those would be 0. So there we go. We've got negative x1 plus 2x2 is equal to 0. So x1 equals 2x2. So that means that x1 is 2 and x2 is 1. So that means my eigenvector for lambda equals 5 is 2, 1. There we go. So that's the first bit done. Now I need to work out my eigenvector when lambda equals -2. Right, so 4 take away lambda is going to be 6. 2, 3, and then we've got -1 take away -2 is going to be 1. Right, so again, I need to make that a bottom element 0. So that's going to be going to be R2 or 2R2 take away R1. Because 2 of these take away one of those would be 0. 0. 2 of these take away one of those is going to be 0. So again, the bottom row is 0. So 6x1 plus 2x2 is equal to 0. So 6x1 equals -2x2. These are both in the 2 times table. 3x1 equals -x2. So that means that x1 equals -1 and x2 equals 3. Because remember, you just take the number that's in front of the alternate letter. Right, so that means that when lambda equals -2, my eigenvector is -1, 3. Okay, so far all I've done in this is find the eigenvalues and eigenvectors of a 2 by 2 matrix. Right, now I've written this down already, that my diagonal matrix D is 5, 0, 0, -2. Right, because that's the matrix made up of the eigenvalues on the diagonal. Now X is the matrix made up of the eigenvectors going down the way. Now, for lambda equals 5 is going down this one because it corresponds to 5 being in this row. So when lambda was equal to 5, my eigenvector was 2, 1. So 2, 1 goes in here. And I need the eigenvalue that corresponds to -2 in here, and that's -1, 3. Okay, so then it told me that the formula is an equals x inverse d to the power of n x. So far, I know what x is, and I know what d is. So I'm really close to getting what I need. What I need to work out, last bit I've got to work out at the moment, is this bit in here. What the inverse matrix of x is. So x inverse is just going to be, it's 1 over, and I'll just write down the formula so we remember it for a 2 by 2. 1 over AD take away BC, D minus B minus C A. Right, that's the formula for a 2 by 2 matrix inverse. So in this case, AD take away BC, so that's 1 over 6 plus 1. Right, A and D swap over, 3 and 2. And B and C become the negatives of themselves, so that's 1 and -1. Okay, I've not swapped these elements around, I've just changed the signs. Right, So that means the x inverse is 1 over 7, 3, 1, negative 1, 2. Okay, so that means that an equals x inverse e to the power of n x. So that means that an is 1 over 7, 3, 1, negative 1, 2, multiplied by 5, 0, 0, negative 2, the power of n, multiplied by x, and x is 2, negative 1, 1, 3. Right, so we're nearly there. We've got our matrices all sorted out and nice. Right, now I need to give an expression for it. Now this will be a 10-mark question, and so far nothing that I've done has been difficult. This is where it's a wee bit difficult. Right, so a to the power of n, and remember what I said, the great thing about a diagonal matrix is that you can take that power inside. A diagonalised matrix, that's 5 to the power of n, 0, 0, negative 2 to the power of n. Remember, put your negative in brackets if you're putting it to a power or doing anything to it. 2, negative 1, 1, 3. Right, now, what I'm now then going to do is I'm going to multiply together these two matrices at the end. Right? And remember, matrix multiplication means you multiply the row by the column, the row by the column, the row by the column, the row by the column. And that's a 2 by 2 and a 2 by 2. So the answer should be a 2 by 2. You can write that down if you want. Okay, I might just do that just to remind you exactly what we're doing. So that was the bit in matrices where we wrote down, hey, that's a 2 by 2 matrix. That's a 2 by 2 matrix. So those two are the same. So we get a 2 by 2 matrix out. Right. So that whole first bit's going to stay the same. I'm not changing that 1 over 7 bit yet. And it needs to stay at the front because remember in matrices the order is important. So now I'm going to get a 2 by 2 out. So I'm going to get an element there, element there, element there, element there. Okay, so this is row 1, column 1. So this is row 1 times column 1. So 5 to the power n times 2. So that gives me 2 times 5 to the power of n plus 0 times 1 is 0. So that's just plus 0. Right, in here. 5 to the power of n times negative 1. So negative 1 times 5 to the power of n plus 0. So plus 0. That's all I've got. Right, then in here. So row 2 times column 1, so that's 0 plus, so that's negative 2 to the power of n. And then here, row 2 times column, so that's 0, and then 3 times negative 2 to the power of n. Right, we're nearly there, he says. Right, now what we need to do is multiply these matrices together. Right, so again, that's a 2 by 2 matrix. That's a 2 by 2 matrix. So what I'm going to get out there is a 2 by 2 matrix. I reckon this is going to be a much wider matrix so I can fit my elements in. I don't know, I'm just feeling like it's going to be. I'm just going to write my elements like this. Right, so that's 3 times 2 times 5 to the power of n. So that's 6 times 5 to the power of n plus 1 plus negative 2 to the power of n. It's that times that. Sorry, that times that plus that times that. Right, now in here, so that's 3 times negative 1 to the power 3, negative 3 times 5 to the power of n, and then plus 3 times negative 2 to the power of n. Looks alright to me. Right then, row 2 times column 1. So that's negative 2 times 5 to the power of n plus 2 times negative 2 to the power of n. And then this row here, right, so that's 1 times 5 to the power of n plus 6 times negative 2 to the power of n. We just have a quick look, see if I've made any mistakes. No, we're looking good. And this is when all my negative signs will have messed up somewhere. Yeah, what's that meant to be there? That must be a plus. 5. Right, okay. So that means that an equals 1 over 7. Well, that's just going to stay the same. There's nothing you can do about that. So that's 6 times 5 to the power of 6 times 5 to the power of n plus negative 2 to the power of n. Right, then you get negative 3 times 5 to the power of n plus 3 times negative 2 to the power of n. Well, that can't be simplified. Although again, everything can be simplified actually. Nah, it can. I suppose you could write that as 5 to the power of n. I'll do that. And that's me done. So that's a to the power of n can be written exactly like that. But what I wanted to know was what's a to the power of 8. So all I'm going to do is swap all my n's for 8 and then type it into a calculator. So that's 6 times 5 power of 8 plus negative 2 power of 8. Take away negative 3 times 5 to the power of 8 plus 3 times negative 2 to the power of 8, negative 2 times 5 to the power of 8 plus 2 times negative 2 to the power of 8, then 5 to the power of 8 plus 6 times negative 2 to the power of 8. Right, so calculator's out. I just type in each of those elements. Right, so if I type in that top element, I get 2, 3, 4, 4, 0, 0, 6. Then and remember, put your negative 2 in a bracket because that's probably where a mistake will happen if I'm going to make one or you're going to make one. So negative 117, 1107, negative 2 times 5 to the power of 8 plus 2 times negative 2 to the power of 8 is negative 780738, and then 5 to the power of 8 plus 6 times negative 2 to the power of 8, which gives me 392,161. Now, obviously, then all we've got to do is divide them all by 7. So 2344006 divided by 7 is 334,858. It is negative 1. That's negative 111,534. And lastly, 5602. So what I've done there is I've been able to find a matrix to the power of 8 by finding the diagonalised form of that 2 by 2 matrix. Now, the power of 8 is difficult enough, but imagine it was the power of 20, power of 30, power of 40. The numbers would be huge, and the matrix multiplication would take forever. Now, I know diagonalising that matrix hasn't exactly been easy, but the only really tricky bit was when we got down to this part here, and we had to do some matrix multiplication. And the reason that looks difficult is because of the power of n on stuff, but if you just treat that as something normal, then it's absolutely fine. Right, now that's the last thing in eigenvalues and eigenvectors. Next week I'll start double integration and we should be finished next week.